Hello and good day to everyone. You're welcome to my YouTube channel. Just kidding. I'm just making this video to as a tutorial to talk about exact and non-exact first order differential equations. I am here representing my big boss and my big boss, Dr. Riddle, and I'm here to talk a little bit or give some tutorial on exact and non-exact first order differential equations. So this is just going to be a short video that you can refer to, study it, and use it to learn about this kind of differential equations. So first off, we know what a differential equation is, and we know what a first order differential equation is. And we have seen like ways of solving first order differential equations. And we have seen the separable method, the linear and nonlinear method. And this time we are going to be looking at the exact and non-exact method of solving first order differential equations. So on my screen, to the left of the screen, you see a PDF. To the right, you see a note, and this is how we are going to do it. We just refer to the PDF and we solve a few questions. And then I also give you try questions so that when you are studying, you try the questions on your own to make sure that you understand it. And I'm going to do my best to explain everything very well for you. All right. So, exact first order differential equation. So, what do we mean by exact? When we say exact, what we are trying to say is that if we have two functions m of xy and n of xy, and we take the partial derivative of the function m with respect to y and take the partial derivative of the function n with respect to x, if they are both continuous, then that is if these two are continuous, then we can say that m of xy dx plus n of xy dy equals 0. And that is what we can say as equation 13. Now, if you look at this differential equation, it is written in the differential form. Now, in solving for exactness or non-exactness of a differential equation, you need to always write it in the differential form. I know that you know what the differential form is and what the standard form is, but I would do a recap for you. So the standard form, you always have the x dy equals a certain function. Let me see. Dy dx equals a certain f of xy. This is the standard form, but the differential form is what we have as the equation 13. So we always want to write our equation in the differential form before we can test for exactness. Now, to test for exactness, we say, according to the equation 14, that if the partial derivative of m, like we established over here, if this partial derivative equals this partial derivative, then we can say that the equation, that is the differential equation given, is what? Exact. So I established earlier that we have two functions, m of xy and n of xy. And what I'm saying is that if we take the partial derivative of your m with respect to your y, and that happens to be equal to the partial derivative of your n with respect to your x, then the differential equation given is exact. One may ask, why are we saying partial derivative of m with respect to y and n with respect to x? Why not m with respect to x and n with respect to y? It really doesn't matter. It all depends on how your differential format of your DE is written. So if you look at our equation 13 in the PDF, you can see that m of xy is the coefficient of the x, and n of xy is the coefficient of the y. So whatever is the coefficient of the x, we differentiate that with respect to y. We take a partial derivative of that with respect to y. And whatever is the coefficient of the y, we take the partial derivative of that term with respect to x. So that is it. And if they happen to be equal, then we say that it is exact. This establishes that if they happen to not be equal, if it happens that they are not equal, then it means that they are non-exact. Then what do we do when they are non-exact? So before we go to non-exactness, I want us to just skip a little bit and come back. Let's try some examples of equations that are exact, see how to go about it, and then we now come back and see what we do when we face non-exactness. So let's look at a few examples. Let's look at the example 1. We have 2xy minus 3x squared dx plus x squared minus 2y dy equals 0. Now remember that I said that the first thing to do is to make sure, if you are testing for exactness, the first thing you want to do is to make sure that your DE is in the differential form. Now, if we look at what we have in this example 1, yes, it's in the differential form because it can be written as, it is written as m of xy dx plus n of xy dy. Okay, so upon comparing, we need to find what is our partial derivative of m with respect to y. So if we know that m of xy is this term right here, this whole term, so we will take that and differentiate with respect to y. Remember that we are differentiating with respect to y because it is the coefficient of dx. So if we do a derivative with respect to y, we get 2x, yep. And then we take the n, right? The n of xy, which is this whole term right here. N of xy is the coefficient of dy. And so we differentiate that with respect to x. Very simple. And if you do that, you get 2x. What do we see here? These are equal. And because they are equal, it is exact. What is exact? The differential equation given is exact. What do we do now? We solve it. How do we solve exact differential equations? So now we have seen how to show that it is exact. The question is, how do we solve exact differential equations? So what you will do is, you will pick one of the terms, either m of xy and your n of your n of xy. The next step is to integrate, okay? Whichever you pick, you have to integrate. And I'll always advise that we know as people who have studied maths for some time now that integration can be quite tricky and unnecessarily long. So we always want to make it simple for ourselves. So we will choose the term which is easier to integrate so that we don't go too long, right? So I would always advise that you integrate the easier term or the more simple term, okay? Looking at our question, comparing our m of xy and n of xy terms, I will say that n of xy is a more simpler term to integrate. So we will integrate x squared minus 2y. Now, in this part of your solution, when you are integrating, you take it along with the dy or the dx that it comes with. So n of xy comes with dy. So we put it dy and then we integrate, meaning that we are integrating this term with respect to y. What does that give us? That gives us x squared y minus y squared, right? Now, you know that in integration without limits, when you integrate, you always have to have what? An arbitrary constant. So ordinarily, you will put in a plus c, right? But here lies a case that we want to solve this equation. We cannot just put in a plus c. It does not follow the normal way. But you put in an arbitrary function. What is this arbitrary function that I am talking about? It is a function in terms of what it is a function just representing the variable that we want to represent. I'm trying to figure out a simple or a less complex way to explain this arbitrary function. But we realize that we picked up our n of xy, right? Let me put so this solution, right? You know that whenever you solve a differential equation, you end up having y equals something, or say f of xy equals something, right? So that is going to be our solution. Ordinarily, this where we have reached now should have been the final end, right? So I'm going to label this as f of xy equals all this, okay? And let me just write this more legibly. So this equals x squared y minus y squared. And I'm talking about an arbitrary function. Okay, so the arbitrary function that we are talking about here is that realize that we picked up n of xy right here, and we integrated with respect to y, right? And if you are doing with respect to y, it makes x a constant. So if we are picking an arbitrary function, we are going to use a function that represents the constant in this integration. So now we have x and y. We have two variables, but we were integrating with respect to y, which makes x a constant. So our arbitrary function is going to be a function of x. And so we represent it by g of x. Okay. So that means that f of x comma y equals x squared y minus y squared plus g of x. Okay. Now we need to find what this g of x is actually, because it's a function. We cannot have a solution containing another function. So we need to find what function it is. So what do we do now? We are going to differentiate at this point. So there's step 3. Now I know that it may seem like a lot of steps, but once you get it, you would understand. So the next thing we are going to do is to differentiate the solution we have, right? So we have f of xy equals all this. So we are going to differentiate with respect to x. Why are we differentiating with respect to x? Because our arbitrary function is in terms of x. If we decide to differentiate with respect to y, it will make our arbitrary function a constant, but we don't want it to be a constant. We want to find it. If it's a constant and we differentiate, it will be 0 and we will not be able to find it. But we want to find it, so we have to differentiate with respect to that function so that it still exists or it is still available for us to solve. So if we differentiate with respect to xy, with respect to x, we have f prime of xy equals 2xy, y squared goes to 0, then plus g prime of x. Why? Because g of x is a function of x. Now we compare. We see that we'll see what we have here. What we are going to compare this to our m of xy and our n of xy. From what we did, we established that m of xy, forgive my bad handwriting, let me try and make it better. M of xy equals 2xy minus 3x squared, and n of xy equals x squared minus 2y. So we are going to take this part here and compare to what we have here. We see that we have a certain 2xy plus g prime of x. Between your m of xy and your n of xy, what contains 2xy? Because we want to find g prime of x. So which function can we compare to f prime of xy that has 2xy that we can simply find g prime of x? And I believe that is your m of xy right here. Right? So we see that we can put it in. That means that we have 2xy. What's left is negative 3x squared. That means that f prime of xy equals 2xy minus 3x squared. G prime of x is negative 3x squared. So now we have this, right? But this is f prime of xy. We want f of xy. All we need to do, so we have g prime of x equals negative 3x squared but we need g of x to find out f of xy. So all we need to do is to integrate both sides. So we have g prime of x. We want to find g of x. So we integrate both sides. And that takes us, and we integrate with respect to x, because g, like I said, is in terms of x. And so when we integrate this, what do we get? We have negative x cubed plus c. And this is our g of x. All we have to do is pick it and plug it into f of xy. So our f of xy now becomes, let me try and use a different, f of xy, which is our final solution, equals x squared y minus y squared. And what is g of x? Negative x cubed plus c. So minus x cubed plus c. And this is actually the solution to your differential equation. I know it may seem a lot, but if you think about it, it was only one page. I just talked a lot. So we have 3 steps. The first step is make sure it's in your differential form. Then you check that it's exact. You can't check exactness if it's not in the differential form. You have to rewrite it. The second step is that if it is exact, we take either of the m of xy or the n of xy, whichever is easier to integrate, and then we integrate it. Upon integrating, we do not obtain a solution with an arbitrary constant, but we obtain a solution with an arbitrary function, which in this case was our g of x. It was g of x because we integrated with respect to y. And so we needed the arbitrary function to be a function of the constant, which was the x. Now that we have it, we need to solve for this arbitrary function. The only way that I know that we can do it is to integrate our solution that we arrived here. Upon integrating, we have f prime of xy to be equal to 2xy plus the, we have to differentiate our solution. So upon differentiating, we have the f prime of xy equals 2xy plus the g prime of x. And the g prime of x is what we need. So we compare that whole statement here to our m of xy and our n of xy. Upon comparing, we realize that we have a 2xy here. And what else is left? Negative 3x squared. That means that g prime of x is negative 3x squared. And we just integrate our g prime to get a g, plug it back into f of xy. We have our solution. I know this has taken so long, but you will find it easy in our next example. I will solve a non-exact, and then we use that to understand this. Now, in our introduction, I mentioned that if you check this condition here, that is the partial derivative of your m with respect to y and your partial derivative of your n with respect to x, and you realize that it happens to not be equal, it becomes non-exact. When it is equal, then it is exact. So if it's not exact, what are we going to do? So that is what we will see here. Let's look at an example. We have 2y dx plus x dy equals 0. That's a funny looking 0. So let's check for exactness. We take the 2y. This represents m of xy. Okay? We have our dx, and this represents n of xy. So we find the partial derivative of m with respect to y. When we do that, what do we get? 2. Then we take partial derivative of our n with respect to x. When we do, what do we get? We get 1. What do we see here? That these are not equal. Because it's not equal, we conclude that it is non-exact. What are we going to do about that? What we will do is that we are going to make it exact. It has to work for us. So we are going to make it exact. How? We introduce what we call the integrating factor. Okay. What is the integrating factor? We know that we've heard of it in non-linear method of solving first order differential equation. However, this is a little bit different in getting your integrating factor. For in exactness, your integrating factor, which I'm going to be using IF to represent, is giving us, that is, the formula is giving us the exponential function to the power of the integral of a certain p of x with respect to x. And then our p of x is giving us your my, that is partial derivative of m with respect to y, minus your nx, that is your partial derivative of n with respect to x, dividing the n function, that is your n of xy. That is your p of x. So let us look at, so I didn't label the steps, forgive me for that. So the first step is to make sure it's in differential form and test for exactness, right? So that is our first step. Our second step is to introduce the integrating factor when it is non-exact. So that is what we are going through now. So let's work towards this integrating factor. This integrating factor, for our question, it says that we are going to have to do some subtractions of the my, which happens to be 2 over here, and our nx, which is this, because the n del x is the same as nx. So 2 minus 1 dividing n of xy, and this is your n of xy, which is x. And this is what we have, 2 minus 1, 1 on x. So our p of x is actually 1 dividing x. And our integrating factor formula tells us that we have to do the exponential to the power of the integral of 1 dividing x with respect to x. At this point, I expect you to know that the integral of 1 on x dx equals ln x. So that is what we are going to have here. We're going to have the exponential to the power of ln x. And we all know that if you are doing integration without limits, you have to bring in the constant c. But in this case, the constant is not coming up yet because it's an integrating factor. We don't need a constant here yet. So e to the power of ln x is just x. I'm not about to explain that to you. So this is our integrating factor. This leads us to step 3. Step 3 tells us that we have to multiply through the differential equation by the integrating factor. So if your integrating factor is actually correct, when you multiply through your whole differential equation, your new equation which you would get should be exact. So our integrating factor is x. So all we are going to do is we are going to multiply through what was given in the question by x. We had 2y dx plus x dy equals 0. If we multiply by x, our new equation would be 2, sorry about that, 2xy dx plus x squared dy equals 0. Now let's test for exactness again. This is now our m of xy, and this is now, this whole thing is now our n of xy. The old is gone, the new has come. So we differentiate this again with respect to y, and what do we get? 2x. We differentiate this with respect to x, what do we get? 2x. Do we see that? Now they are equal, hence exact. Amazing, right? So this is our new equation that we are going to be dealing with. Because it is exact, we go ahead and solve it the way we solved the other one. So we have 2xy. I'm just going to flip because my page is full. 2xy dx, 2xy dx plus x squared dy. So if you didn't understand the first question I solved on exactness, please follow keenly on how I'm going to be solving this, because I am more or less going over the method of solving exact differential equations. So let's go ahead and solve this. Now that we know that this is exact, what did I say? We pick the easier term and integrate. Remember that point. Integrate the easier term. Look at 2xy and we look at x squared, which is easier to integrate. For me, I will say x squared, okay? So we do integral of x squared and we pick its corresponding dx dy, which is dy. So meaning we are integrating with respect to y. Alright, am I sure I picked I think I did not pick the easier term, so I'm going to change it. Whatever you feel like, do it. Make sure that you are ready to pay the consequences. So since I'm picking 2xy, it means I'm going to be integrating with respect to dx. Now, if I integrate, I think the decision I made first was correct. Oh, forgive me for my confusion. I don't want to make my own life difficult. So we take the integral of x squared dy, and if you do, I think they are both fairly confusing to a point, but we are able. So our solution, f of xy equals x squared y plus c. Is that right? Not necessarily. It is not completely right. It is not plus c, like I said earlier, that we, instead of an arbitrary constant, we introduce an arbitrary function, right? Good. So what is this function going to be in this case? Since we integrated with respect to y, our arbitrary function will be in terms of x. So we represent that as g of x. Now we need to find g of x. What do we do? So we differentiate with respect to x. Okay, so we will have f prime of xy equals 2xy plus g prime of x. Awesome. We are seeing 2xy again. Where did we see it first? We saw it in our m of xy right here. Our m of xy right here. And so, what do? We compare. In comparing, we see that our m of xy was 2xy plus what? Plus nothing. It's just 2xy. So let's say plus 0. What does that mean? If we have another 2xy plus g prime of x, it means that g prime of x equals 0. So now we have to integrate both sides with respect to x. So we have g of x equals integral of 0 dx. What is integral of 0 with respect to x? It's just going to be 0x plus c, which is just 0 plus c, which is c. Now we get back our arbitrary constant, and we just put that in our solution right here. So we would have x squared y, that is, we will get our solution f of xy to be equal to x squared y plus c. And this is the solution to what was our non-exact question right here. So you see, this was just 1.5 page. It's just that I write and talk a lot. But when you solve, you realize that this is pretty simple and you'll be able. So to test your knowledge, I'm just going to give you 2 questions to solve by yourself. Please do try and solve. It will help you understand this better. For my first question, I give you the differential equation cos x minus x sine x plus y squared. Plus 2xy dy dx equals 0. And for the question 2, I give you x squared plus y squared plus x dx plus xy dy equals 0. And I'll give you a couple of hints. I'll say, remember to write in differential form, and also remember your trig. And you are good to go. This is very simple, and I really hope you'll be able to do it. And if you have any questions, you may ask. Alright, have a great rest of your day, and see you another time. Thank you. Bye.